In other scenarios, you will be provided with an equation that contains some of the information already provided, such as a of t equals p times 1.5 to the t, where a of t is the population at some time t, p is the initial population, t is the time in years after the initial population was measured, and 1.5 can be translated into 1 plus 0.5, which means that the growth rate was 0.5 or 50%. Let's use this model for the next questions. A of t equals p times 1.5 to the t power. If the initial population is 4 million, what will the population be after 1 year? So we plug in 1 for t, and we plug in 4 for p, and we get A equals 6 million. If the initial population is 4 million, what will the population be after 6 years? So now we plug in 4 for p and 6 for t, and we get that A equals 45.6 million. If the initial population is 4 million, what will the population be after 5 months? You might think that you could just recall that after 1 year the population is 6 million and it started at 4 million, so after half a year it would be 4 million plus 5/12 of 2 million equals 5.83 million. But that would only be true for a linear model, while this problem is exponential, so this is not correct. Discuss possible solutions. We convert the formula to provide monthly results by raising the rate to the power of 12t rather than t, so that when we put in the number of years as t, it converts that to 12t months. In order not to change the amount after 1 year, I have to take the 12th root of the rate, so that the equation is still true. So A of t equals 4 times 1.5 to the 1/12th power raised to the 12t power. Note, the properties of exponents shows that 1.5 to the 1/12th power raised to the 12t power equals 1.5t. So A of t equals 4 times 1.0344 raised to the 12t power. We substitute t equals 5 over 12 since we are looking for only 5/12ths of a year. If we substitute t equals 5 over 12, since we are looking for only 5/12ths of a year, 5 months would be A of 5/12ths equals 4 times 1.0344 raised to the 12 times 5 over 12 power, which simplifies to the 5th power because the 12s cancel. A of 5 over 12 equals 4.74 million people. Instead of changing our exponential base to solve the problem, we could also change the form of the exponent. In our original problem, our function was A of t equals 4 times 1.5 to the t, where the value of t is measured in years. To convert and be able to substitute months, we must divide t by 12. So A of t equals 4 times 1.5 to the t over 12 power. Using our new equation representing t in months, we can substitute and continue the calculation. A of 5 equals 4 times 1.5 to the 5 over 12 power. A of 5 equals 4.74 million people. How are these methods similar? How are they different? Which method do you prefer? Discuss these questions in your groups. If the initial population is 4 million, what will the population be after 15 months? There are two ways to solve the problem. We can either raise 1.5 to the 1 over 12 power and then raise that to the 12t power, or we can just raise 1.5 to the t over 12 power, which you can see is much simpler. And we get as our answer 6.64 million people.